Hi, my name is Gayatri Menon and I study mechanical engineering. My job in the team this semester is to be in charge of the prototype and the manufacturing of the design. I will also be looking at some of the logistical parts as we are a team of two at the moment.
My name is Maddie, and I'm a chemical engineering major concentrating in biotechnology. My main role in medical is to work on the chemistry behind our reactions to make sure that they're endothermic.
Our graduate advisor was Jonathan Gosine. He got his bachelor's in mechanical engineering with a concentration in robotics and automation, as well as a master's of science in mechanical engineering with a focus of biorobotics. He is currently pursuing a doctorate of philosophy in mechanical engineering, with a focus in rehabilitative robotics. In times of crisis, entire countries can go weeks or even months without power. For example, in Puerto Rico following Hurricane Maria, the power went out for 6 months and left at least 900,000 people without power, making it nearly impossible for people at home to refrigerate medicine even when there's a sufficient supply. The lack of consistent electricity and transportation makes it even more challenging. So we asked, how might we improve the storage of insulin for diabetics that have lost power and equipment in Caribbean countries that have been recently struck by a natural disaster? We thought about those who may be affected and came to the conclusion that we need to give them a solution that was affordable, long-lasting, easily accessible, and most importantly, could be used without power. Currently, there are many different solutions to this problem. However, most of them require that whatever product is being used needs power, whether it be a battery source or from a power outlet. This can definitely be a struggle for people living in the Caribbean and places without power security where they don't have access to power very consistently. We plan to overcome this by using a chemical reaction rather than electricity. This would enable us to make sure that the product is actually being cooled while the medicine is still inside at all times, rather than only while the product is being connected to a power source.
In this experiment, we tested 3 salts that we believe were most suited to be used as a coolant: ammonium nitrate, ammonium chloride, and sodium bicarbonate. We selected these 3 salts because of their reactivity with water. All 3 salts have a large bond radius, high hydration energy, and low lattice energy. Simply put, they are weakly held ionic salts that dissolve in water fairly easily. When dissolved in water, the ionization of these salts is endothermic. An endothermic reaction takes in energy from the environment to force the reaction forward, lowering the temperature of the overall solution. A diagram illustrating how a salt dissolves in water is shown on the bottom right. During the experiment, we dissolved 10 grams of each salt into 100 milliliters of water and measured the temperature difference. As you can see, ammonium nitrate has the greatest temperature difference because it has the highest heat of solution. Moreover, it's a relatively common household item found in breakable ice packs. Sodium bicarbonate is probably the second most suited salt for our purposes because sodium bicarbonate is also a common household item found in baking soda of around 99% purity. But it has a relatively low heat of solution and low solubility in water of about 10% by moles. Ammonium chloride is probably the least suited because of its low heat of solution and difficulty to acquire in areas with poor infrastructure despite its high solubility. For these reasons, I believe that in the continuation of this project, we will focus our attention on the use of ammonium nitrate as our primary coolant.
We wanted to choose the Caribbean as a starting point for our venture because we wanted to target an isolated location who experiences natural disasters that enables them to not leave their location. Islands are particularly vulnerable since once their main power grid goes down, there is no power for anyone there and can cause a huge risk for those who need refrigerated medicine. Large countries such as the US and European nations can afford to evacuate citizens, but those who live on islands either full-time or can't afford to leave are put in danger. Furthermore, we wanted to target an area that wasn't as developed as the US, where there was more room to expand on solutions and problems in a cheap way. The Caribbean is an ideal location for us to start as there would be very many customers who would be interested in a cheap way to make sure that they can keep their medicine cool. At this point, our biggest selling point is the fact that our product would be a lot cheaper due to the materials that we use in our product as well as our easy method of distributing it. Our competitor products are mainly focused on getting their products to higher class people who can afford the technology that went into these items. This was the first potential design idea that we had. With this, the user just had to mix the chemicals by putting them both into the slots as shown. The problem with this is that the chemicals would have been exposed and the person would have to deal with the reaction themselves. Thus, I came up with this idea. This allows a tube to run through the sides of the box that has an insulating material on the outside and a conducting material on the inside, allowing the coal to go into the box and for it not to escape. In the pink area, we would have one side of the chemicals, while the user inserted the other chemicals into the tube from one of these entrances. This allows us to control the portion of the chemicals that are mixing together based on how porous we decide to make the tube. In our actual design, the tubes will be a lot more prominent in the side of the box to allow a greater surface area of the chemicals to interact and thus create more of an endothermic reaction that will keep the box cooler.
The next issue for our team to explore in the future is how long will our solution stay cold, or to put it more scientifically, the rate of heat transfer from the coolant to the insulin and from the air to the coolant, where Q is the total heat transferred, H is the heat transfer coefficient, T sub A is the temperature of the air, and T sub S is the heat of the system as a function of time. I was going to calculate the rate of heat transfer to eliminate the time for one batch of coolant. However, the heat transfer coefficient is a function of surface area, which will depend on our prototype cooler design. However, because of the high solubility of ammonium nitrate in water, we can manipulate our design to have the highest internal temperature while decreasing exposed surface area to slow the rate that the cooler warms up.